Hey guys, so welcome back. In the previous video we saw the derivation for electric field due to a charged plane sheet, an infinite sheet. So this will be the final video for this chapter, the concepts of this chapter, and in this video we will see the derivation of two applications of Gauss law. The first one is electric field due to a spherical shell that is hollow on the inside, and the second derivation is actually not a part of the textbook, but by doing this derivation we'll be able to answer some numericals since they both are based on the same concept. You don't need to learn this in the examination point of view. Okay, so the second derivation is the electric field due to an insulating solid sphere. Okay, so now let's start with the derivations. Okay, so now let's talk about a spherical shell. So there are two cases within the spherical shell, and that are first one is outside the shell and second is inside the shell. And when it's a shell, it means that the interior is hollow. That is, this is a shell with the interior being hollow. So if you're giving it a charge, the charge is always going to reside on the outer part. That is the part where there is mass, not on the interior. So this charge distributes itself over the entire surface area, and let's say the sphere has a radius of capital R. So this radius is capital R, and now let's consider a point P over here at a distance of small r. We need to find the electric field at point P. Let's consider this the outside case. So the first step, as always, is to draw the Gaussian surface. When it is already given as a sphere, the easiest Gaussian surface to draw is a sphere. So let's draw a sphere containing the point P. And it's important to remember the fact that it should contain the point you're considering. So this is the sphere. Now, in the previous case it was a cylinder. That means there are different faces. There is a curved surface area, then there is the two circular ends. So we separately had to take phi1, phi2 as fluxes. But in this case, a sphere is symmetrical about every point. So we can just generally take it as flux. So we are directly going to the step that flux equals charge enclosed by epsilon naught. So what is flux? E dot s, or Es cos theta. But the speciality of a sphere is at any point, if you draw a line, it's always going to be perpendicular. This is the concept of tangents. So it's just going to be Es. E dot s equals q by epsilon naught. Now, what is the charge enclosed within the Gaussian surface? In this case, we are going to again use the concept of surface charge densities. Surface area is the total charge enclosed divided surface charge density is the total charge enclosed by the surface area. But here we need to make a clear distinction. That is, this is not the same surface area as this formula. That is, the left hand side of the equation is the total flux passing through the Gaussian surface. So remember that LHS is for Gaussian surface and RHS, all the terms in the RHS, that is Q, is for the given body. So you must keep this in mind. That is, the terms in the LHS, the surface area in the LHS is given for the Gaussian surface. That means to find the surface area of the Gaussian surface. But the right hand side, the charge enclosed, is by the given body. Yes, it is the charge enclosed within the Gaussian surface, but it's not the charge present in the Gaussian surface. It's the charge due to the given body. So let's substitute the values according to that. Just keep this in mind. So sigma equals q by surface s. Okay. So E dot, this surface area is that of the Gaussian surface. That is 4 pi small r squared. 4 pi small r squared equals q is equal to sigma into s. Sigma into, here s is 4 pi capital R squared, because you're finding the unit surface charge density for the given sphere, that is at this point, this point, this point. So that's going to be q by 4 pi capital R square. So q is equal to sigma into 4 pi capital R square divided by epsilon naught. Now let's try to find the value for epsilon. So electric field. Electric field is going to be sigma into 4 pi and 4 pi cancels off. I'll just cancel out off in the next line. So sigma 4 pi capital R square divided by 4 pi small r square into epsilon naught. 4 pi, 4 pi. So you're left with sigma by epsilon naught into capital R square divided by small r square. This could be your final step, but if you want, you can substitute back the value for sigma. So when you substitute back the value for sigma, it's just like redoing or undoing the step. Because over here, we substituted the value for q, but now we are substituting back the value for sigma. So what's the point? Well, it depends on the situation. If they have given you the value for surface charge density, then you can directly use this equation. But if they haven't given you the surface charge density, you'll have to use the next equation, that is, we know that from, I'll just write it over here, surface charge density is the charge divided by 4 pi capital R square. So now we are going to substitute that over here. 1 by epsilon naught R square by R square into sigma is q divided by 4 pi R square. Cancels, cancels. So you're left with the equation, I'll drop these off, that electric field at any point outside is 1 divided by 4 pi epsilon naught into q divided by R square. And if you recollect this, this is very similar to the formula for electric field due to a single point. I'll also write the other formula if we had to use that. Sigma divided by epsilon naught into R square by R square. So this formula is very similar to that of a charge due to the electric field due to a single point charge. That is, as if you are considering this entire shell to be a point charge. You're considering this to be a point charge, and then you're finding the electric field at this point P. That is what it looks like, but this is the actual way to derive it. So we have finished the outside part. Let's quickly look at the inside. It's not a big deal. So let's just rub this off. The outside is completed. Now let's look at inside. So the only difference in inside is where you place the point P. So I'm going to place the point P over here at a distance again R. So let's try the formula. Flux is equal to Q by epsilon naught. E dot S is equal to Q by epsilon naught. And the reason I'm doing fast is because you should be knowing. Equals, what is the charge enclosed by this Gaussian surface? After we construct the Gaussian surface, what is the charge enclosed over here? It's 0. Because all the charge is lying on the surface. There is no charge inside the Gaussian surface containing point P. So charge is 0. So electric field inside equals 0. Electric field inside a spherical shell is 0. So this is the conclusion. If there is no charge inside the Gaussian surface, the electric field is 0. Let's next look up, this derivation is actually not there in the textbook, but it has been a part of the question. So let's also look at this derivation. So once you're done with this, you'll be completely thorough with how to draw a Gaussian surface and how to. This is a special derivation because you'll notice it how the charge distribution is different. Previously, we always took charges which are completely lying inside the surface or come outside, but we have never considered a point P where you do not know how much charge is inside based on volume. That is, so this one is called the insulating sphere, and the reason it's different is because the charges do not lie outside, they lie inside. For a conductor, the charges will want to go away from the metallic body as fast as possible. They want to be conducted, they want to transfer. But for the insulator, it always lies inside. That's the reason why insulators are bad conductors of electricity. So this is how the charge distribution is going to look like. It's a solid body. So now let's say I have to find a point, electric field at a point P, which is over, this is the center O of radius capital R, and let's say I need to find the electric field at this point P, which is at a distance of small r. I'll draw the Gaussian surface with a different colored marker. The step one is always to draw the Gaussian surface. So this is the Gaussian surface, the green colored circle. Okay, so let's go ahead with the formula. That is, what is the total flux? Total flux equals the electric field times the surface area. Electric field times the surface area of the Gaussian surface. The flux is the left hand side, right? The flux is always for the Gaussian surface. So what's the surface area of Gaussian surface? 4 pi small r squared. Equation number 1. So now we have to find Q by epsilon naught, and here's where the problem comes. The total charge in this sphere is Q. That's a given quantity. But what is the charge in this part? In the previous cases it was linear charge density, surface charge density, so it was easy to find. But what about a volume charge density? Volumetric charge density. So that's the concept you're going to apply here. The assumption you make is that the volumetric charge density is uniform about every point. So if you take a point over here and if you take a point over here, let's call this A and let's call this B. The volumetric charge density rho at point A equals to the volumetric charge density at point B. This is the meaning of it. It's uniform about every point. So now we just want to find the volumetric charge density inside the sphere. Once we know that, we can find out the charge residing inside the given Gaussian surface. So let's just substitute. Inside, volumetric charge density inside the given sphere equals to volumetric charge density inside the given Gaussian surface equals to volumetric charge density of the total sphere. It's a charge density, doesn't make a difference. So the reason why we are doing this is we need to find how much charge is present inside as a function of how much charge is totally there. So what is the volumetric charge density? You know the formula for rho. This total charge present is Q. So rho is equal to Q divided by V, isn't it? So Q inside, that is charge present inside the Gaussian surface, divided by the volume of the Gaussian surface, which is 4 by 3 pi r cube, equals the charge total of the sphere, which is Q, divided by 4 by 3 pi capital R cubed. So 4 by 3 pi cancels off. So now we get the function, that is how much charge is present inside. So amount of charge present inside the Gaussian surface, which is what we need to substitute in the Gauss theorem, equals the total charge times R cubed by capital R cubed. This is the equation we need. That is, now we know how much charge is present inside the Gaussian surface we have constructed. And how we found that out is by equating the volumetric charge density inside the Gaussian surface to the volumetric charge density of the entire sphere. So this is the equation we needed, and now let's proceed with the formula. Now it's all just direct substitution, except there's one more difference. So flux total equals Q by epsilon naught. It's the general formula. So let's try to substitute. Total flux is E dot 4 pi r squared equals the charge enclosed, which we have the formula, Q times R cubed by capital R cubed divided by epsilon. But here's the difference. This is epsilon. Epsilon is free space. Epsilon is vacuum. But here is a medium. We don't know what is the medium. It could be metal, it could be a copper, it could be iron, but we don't know what is it. So we are going to use relative permeability. Sorry, relative permittivity. We have already seen in the first lecture, that is epsilon of the given medium, which you do not know what it is epsilon r times epsilon naught, where epsilon r is the relative permittivity of the medium. So in place of epsilon naught is given that it is a vacuum, because in most of the cases it's vacuum, but generally it means the permittivity of whichever medium you kept it in. So the permittivity of this medium, which is ER times E naught, and this is it. You just have to simplify it now, and we are left with the formula E equals QR cubed divided by ER E naught capital R cubed into 4 pi small r squared. R squared and R cubed remains 1R, and that's it. So you get QR divided by 4 pi epsilon naught epsilon R R cubed. If you want to rearrange it, it becomes 1 by 4 pi epsilon naught times Q by epsilon R times R divided by R cubed. And this is the electric field inside a insulating sphere. This is not given in the textbook, but the reason we did this is because now we clearly know how to draw a Gaussian surface, how to find out what's the left hand side of the Gaussian theorem, that is the flux, how to find the right hand side, what surface area is supposed to be given for the left hand side, and what's the total charge present within a Gaussian surface. And this is the perfect example to understand that. So this is the total electric field. But now it's a very simple question, but you can answer it by yourself. What if I had to find the electric field at this point P? Now how am I going to do it? We can do the entire process of this again, drawing a Gaussian surface, but instead, since all the charges lie inside it and it's a complete closed sphere, you can consider this as a point charge. So I'll just rub this off. This is the final answer. So you can consider this entire sphere as a point charge of the charge Q. So this entire sphere can be considered as a point charge, and this point is over here. And now we know what is the electric field, which is F by Q, the basic formula, which becomes 1 by 4 pi epsilon naught, the charge Q divided by the distance R squared. So this is outside the sphere. So unless the point does not lie inside along with the sphere, you can treat it as a positive charge, as a unit charge. Thank you guys for watching. So this video was the last conceptual video of this chapter. The next video I'll be doing some questions based on this chapter from the textbook and some in-text examples. If you have any doubts, any suggestions or academic questions, you can drop it at my email, which is physicsorbit1@gmail.com. I'll be happy to answer them all. Thank you.